So instead, P1 zeros all but the first two entries in the first column of A. So P1A is now going to have two non-zero entries. I've joked for years that I need just a stamp that puts in all these X's. Okay. So now I've made at least a lot of a first column zero. But in order to do that, this affects only rows 2 to n. So now I apply the same household reflection on the right. This is going to affect columns 2 through n. So all the zeroing I did in the first column is now preserved. And the eigenvalues are preserved too. Okay. So now we have an approach. So now our goal is to use householder reflections to make this matrix T naught, which is U transpose A U, an upper Hessenberg matrix. I've mentioned upper Hessenberg matrices before when talking about GMRes. Okay. So a matrix it's one step shy of upper triangular. So T naught ij is equal to 0 if I is greater than j minus if I is greater than j plus 1. So, because on the main diagonal, I equals j. On the subdiagonal, I is equal to j plus 1. And then below that, I is greater than j plus 1. So all entries below the first subdiagonal are equal to 0. So we have a structure like this. So I have in column J, you have j plus 1 non-zero entries. So you still have this non-zero subdiagonal here, and then the upper triangular part. So that's possible. We can go ahead and reduce it to upper Hessenberg form, and that is really going to help us to speed up the iteration. At least each individual iteration, we're still going to have slow convergence all told, because those iterations will be the same, but the work done within each iteration will be much less. So let's take a look at that. How do we do QR factorization on an upper Hessenberg matrix? I have to remind myself that I don't have to get through absolutely everything today. All right. So if we take a look at specifically Hessenberg QR. So all you need to do, this marker not feeling so good about it. So you need to zero only n minus 1 subdiagonal entries. people on the coast, is the red writing still showing up okay? All right, I think someone told me I couldn't use red, but I don't know.
Looks pretty dark to me.
Yeah. That like it wouldn't go well over a projector or something. So all we need to do that is n-1 Gibbons rotations. So we're not going to use household reflections for QR in this case because we only have one entry per column to wipe out. A Gibbons rotation would be much more efficient in that because a household reflection is very destructive. It'll wipe out a whole bunch of entries in a single column. We only have one entry per column to get rid of. We'll just rotate 2 rows to make that entry 0. So now each Gibbons rotation will only affect 2 rows in their entirety. So we have n-1 Gibbons rotations, order n work each, so order n squared floating point operations overall. Okay. And actually this applies for the QR factorization. We'll take that little time. And multiplying the factors together in reverse order, also order n squared time. And the reason for that is for the QR factorization, getting rid of these subdiagonal entries, we use row rotations. In order to get our upper triangular matrix RK. But there's another way to think of it is RK is equal to UK transpose TK minus 1. So this UK transpose, that is a product of row rotations. But then what we do is apply those same rotations as column rotations on the right. So that's what's happening here. So in other words, the amount of work to pull this off and this off is basically the same. So now we've cut down the work by an order of magnitude, order n squared work per iteration instead of order n cubed. We're still taking too many iterations, but we'll tackle that problem later.
What about getting a upper Hessenberg? Is that just that after we start with an upper Hessenberg matrix?
Yeah, this only applies to once you have an upper Hessenberg matrix to work with.
Okay.
To get an upper Hessenberg matrix, that is still expensive.
Yeah,
it's order n cubed work, but you only have to do it once.
Oh, okay.
And also the number of iterations in total that you take after you get to Hessenberg form, to get all the eigenvalues, it's still going to be roughly order n iterations. So we're still going to do order n cubed work for this.
Okay.
So,
Yeah, so it doesn't.
yeah. So the pre-processing and the iteration, about the same.
Okay.
Well, in the unsymmetric case. So one thing I should mention here is, in the symmetric case, it's order n. And the reason why is, what?
Go ahead.
I think you might have said it.
Because then it's tridiagonal.
Yes, that's exactly what happens. Because in the symmetric case, so Hessenberg plus symmetric is tridiagonal. And so what that means is, you're still doing n-1 Gibbons rotations, but each one of those rotations does less work because there's fewer non-zero entries to modify. So in that case, the reduction to tridiagonal form is still order n cubed time, but once you have that tridiagonal form, it's also erases. So, and the symmetric eigenvalue problem is so much easier because you know you get real eigenvalues, a lot of simplifications come about from that. Okay. So, let's see, I'm doing timelines. Okay, so I have enough time to describe this Hessenberg QR stage in more detail, and then the next thing would be the actual reduction to Hessenberg form, but we might not have time for that today.